We're going to continue our discussion of solving differential equations of this form right here. Now, what we've done so far is we've used this method called undetermined coefficients. And it's very similar to this, but there were some requirements for undetermined coefficients. One of the requirements was that these coefficients had to be constant. Okay? And also, we needed to be able to come up with a function g of x that an assumed solution function that was similar to this. In other words, that fit a table. Like, for example, if this were 3 cosine x, we would need to use an assumed solution of a cosine x plus b sine x, that sort of thing. Well, this variation of parameters that we're going to look at doesn't have those assumptions necessarily. However, we're still going to primarily in practice use this method when we do have constant coefficients. So we're going to solve equations like this, and the ones we're going to solve are going to have constant coefficients, although that's not necessary. But let's go back, and I want to motivate how this method is used and how it works. Let's think back at a linear first degree or first order differential equation. Here's a linear first order differential equation of this form. Now remember, we had the integrating factor that we found. Remember this, the integrating factor. Now, if you think about it, if you look at this, just look at the homogeneous case here. Okay. So in other words, if I put a 0 over here, what you're going to find is that this is actually a solution for the homogeneous case. So in other words, this is the integrating factor. And if we replace, if we instead put a negative up here, change the sign, we'll find that this is actually a solution for the homogeneous case. And you can check that out. You can say, well, let's try that out. I'm going to take the derivative. Okay, here's the derivative. Okay, and I'll just plug that in. See, I've got this. I plug this in for the y prime. Okay, and there you go right there. And then for the py, I've got this. And you'll notice, that does indeed equal 0. So we see that, yes, this is a solution for that linear, for that homogeneous case. Now, what I want to do, though, is I want to go back and I want to solve this differential equation, okay, and just go back to the way we solved using the integrating factor before. Notice I multiply both sides by the e to the integral p dx. I multiply both sides by that. And here's what I've got. Okay. So this is you got to hearken back to what we did a couple of weeks back. Now, going through this process, integrating both sides, what you'll find is the yp is equal to this. Okay. Just using that method. And notice, let's just take note here, this is the solution right here of the homogeneous case. You just notice that. Okay? And then we've got this in here. Now, what I want to do is I want to rewrite this way. Okay? So you notice all I did was I said, well, I could replace this e to the integral of pi dx with a negative, and I put it on the bottom. And now notice we've got this. This is our solution right here. This is our particular solution. Okay? Now, what I'm trying to do is motivate why this method that I'm going to show you is going to work. And I want to start off with this linear case. But you can see that, yes, I've got the homogeneous solution here, and I make this multiplication, and that's the particular solution. Now, let's do this. Let's suppose that the particular solution is u sub 1 times y sub 1. In other words, this right here is a function of x, u sub 1. And I want to say that y1, let's suppose that is a solution to the homogeneous case. Let's suppose that's the situation I've got here. So what I have here is I know the homogeneous solution here, and I'm going to multiply that by u1. And I'm going to say, I wonder if I can find a u1 that will make this a particular solution. Okay? So what I'm trying to do is find a particular solution, and I've got a homogeneous solution there. Okay? So let's see how this goes. Let me take the derivative. Okay? So there I've taken the derivative, and now what I'm going to do is I'm going to plug back into the function. So this right here is y prime, and I put it right here in place of y prime. And then I've got pu1 y1 equals f of x. Okay? So I just plugged back in. I plugged this in right here in place of y, and I plugged right here the prime. And now let's go through this process here. Notice that this part right here, remember y1 is a solution to the homogeneous case. So this right here is 0, right? It's 0 because this is y1 prime plus py1, and that is just this. And it's a solution to the homogeneous case. So that means that part is 0. So what I've got then is I've got this situation. It all boils down to that. Now what I want to do is I'm trying to find u1. So I've changed u1 prime to du1 dx. I'm going to work with differentials here. So I multiply. I've got this now. And then I integrate both sides. See? I integrate it, and I get this. Okay? Now dig this, that this is my homogeneous solution. Just like up here, this was my homogeneous solution. I've got my function up here. Here's my function. And now, remember, the particular solution is the homogeneous solution times this thing. So here is my particular solution. And so you can see, if I know the homogeneous solution, I can get a particular solution this way. Look at that. Now, you can see the process then. What we did was we replaced, instead of putting C1, Y1, I said, well, what if I just put a function here? Okay, U1, and now I can find out what U1 is. So this kind of shows you how the process can work. Now what I want to do is I want to look at a differential equation like this one. Notice it's second order. And this time I'm going to say this. I'm going to say, let's suppose that a complementary solution, in other words, a solution to the homogeneous equation is this. This is a solution to the homogeneous equation. Okay? Now, I'm going to use the same reasoning, and I'm just going to say this. I'm going to speculate that perhaps I can find a particular solution by replacing these constants with a function, u1 and u2. I wonder if I can find a u1 and u2 that will give me the particular solution. Okay? So notice all I've done is I've replaced the c1 and c2 with functions of x. u1 is a function of x. It's not a constant. u2 is a function of x. Okay? Now I take the derivative of that. Okay? Here's my derivative. Just using the product rule. Okay? And then I take the derivative of this, and I get this thing right here. Okay? Now, I did this in advance because I'm cognizant of the time. I don't want to take up a lot of time writing this out. But you can see I've just taken the second derivative. I've taken the derivative of this and got the second derivative. Okay? Okay, now, I'm ready at this point to plug back in, but here's what I want to do. I've got my first derivative here, and I want to multiply this by p. So I've got that right here. I just multiplied by p. And then I've got the initial function right here multiplied by q. So I put that here. Okay? So my differential equation is y double prime plus py prime plus qy. Okay? Now all of these terms here are what I need to add together, and they should equal f of x. And I want to find out, well, what is it possible that all this mess here ultimately equals f of x? In other words, is there a value for u1 and u2 that will make all of these terms equal f of x? So I'm going to add things together. So I'm adding all of these terms up, and I'm grouping them. Okay? So you notice what I've got here is I've grouped some terms here. I've got this term right here with that term, and then this term. And I've put all of those right here, and I've factored out the u1. Okay? Now I've done a similar thing, grouping some other terms with u2, and I've put all those right here. Okay? So I'm just grouping things together, and then I just wrote out all the other terms. Okay? So here's everything else. Here's everything else I've written out here. Okay? All of those. But you might ask, well, why did you group these together? Well, remember, y1 is a solution to the homogeneous equation. That means that this right here is 0. And it also means that this right here is 0. Both of those are 0 because y1 double prime plus p y1 prime plus q y1, that equals 0 because y1 is a homogeneous solution. y2, same thing. So both of those are 0. Now, the next thing we do, you'll notice that of these terms that are remaining, now you realize that these terms right here are gone. Okay? Now I'm just dealing with these ones. These ones right here. Now, I want to look at this and this, these two terms. And I'm going to rewrite those this way. Notice I've got u1 prime y1. These two terms right here. And what I'm going to do is I'm going to say that's the derivative of u1 prime y1. See? So dig this. Let's just take the derivative of this. I've got u1 prime y1 prime plus u1 double prime y1. Not y1 prime, but there we go. And you'll notice that this right here is the same as this right here. Okay? Now, I also did the same thing with these terms. And I put those right here. Okay? So that's what I've got so far. Okay? So I just put those down here. And now I'm going to Okay, so, and then I just put all the other terms together, okay? Now, you'll notice that this right here, these two things, the derivative of this plus the derivative of this, I could just write this way. Okay? You know, it's the same thing. That's a property of derivatives. See, the derivative of this plus the derivative of this equals the derivative of those two things. Okay, so I've got that right here. Now, then I grouped some other stuff together. Notice I grouped the coefficients of the p's. See, I grouped that together right here. Okay, and you'll notice that u1 prime y1 plus u2 prime y2, that's in both of these. And then I've just got this left. Okay, now here's what we're trying to do. We're trying to find a u1 and a u2 that make the particular solution. And here's the trick. This is what we do. This is a trick here. We're going to make an assumption. We're going to assume that u1 prime y1 plus u2 prime y2, we're going to assume that that equals 0. See? We're going to make that assumption. And you might think, what'd you do that for? Well, because I need two equations. I've got two variables, u1 and u2, and to figure out what u1 and u2 are, I need two equations. Now, I've got this equation right here, okay, which is right here, and now I've got this one. Because I make this assumption, now I have a system of linear equations that I can solve. I can solve for u1 and I can solve for u2. See? Just a system of equations. Now, what I'm going to do to solve these is I'm going to use Cramer's rule. I'm going to use Cramer's rule, and you can go back and review Cramer's rule if you want to, but what it amounts to is I'm solving this system of equations. And what I'm going to do is I'm going to say u1, I'm going to solve for u1 prime first of all. Okay, so here's u1 prime. That's in the first column. So what I'm going to do, now notice on the bottom here, all I've got is y1, y1 prime, y1, y1 prime. Here's y2, y2 prime. And that's on both of these, y1, y1 prime, y2, y2 prime. Okay? The bottom is the same for both of these. However, up top, since I'm solving for u1 prime, the column of u1 prime I'm going to replace with this, 0 and f. And then the other column is just like the bottom. Okay? Now I do the same thing for u2 prime, except now the column with u2 prime is the second column, so I replace the second column with 0f, and the first column stays y1, y1 prime. Okay, now, what we do now is, this is our formula. This tells us how we can solve for u1 and u2. See, we've got a formula now. Remember, our whole goal was, I wonder if I can find a particular solution just by, writing it this way, if I know the homogeneous solution. Well, it looks like we're right at the border of that. So let's see how this works. Let's suppose that we have a differential equation right here. Okay? And what I do is I use the auxiliary equation to find the solutions for the homogeneous case. Okay? So I'll get y1 equals e to the 2x. And since it's, multiplicity 2, the y2 is x e to the 2x. So here are my homogeneous solutions. Okay? Now, I want to find u1 prime. Okay? So dig what I'm going to do. I'm going to put, look, 0f Here's 0 and this f function over here. Okay? And then I've got y2 prime. And then down here, I've just got, y1 prime, y2 prime. Okay? And these are determinants. So remember, I go this multiplication minus this one. So 0 times this minus this. And I get this right there. Now down at the bottom, I have main diagonal. This product minus this product. See? So you see it right there. And when you work this out, look what you get. You get negative x plus 1. Okay? So dig this. Here's what we've got. u1 prime equals negative x squared minus x, just distributing here. Now, I don't want u1 prime, I want u1. And here is the problem with this method. This is one of the problems. You have to integrate. And sometimes you'll get something that's a challenge to integrate. So this is a weakness here. This might cause you some vexation. But this one is easy to integrate. You got u1 prime equals, this thing. So u1 is equal to this thing. A baby could integrate that. So we got a nice, easy integral there. Okay? Now, I go through the same process for u2 prime, and I get x plus 1. So I got u2 prime equals x plus 1, another integral a baby could handle, and you get 1/2 x squared plus x. Oh my goodness. We've got u1 and u2. So look at what we've got. We've got y sub p, there's u1, y1, plus u2, y2. So there's the particular solution, and here is the homogeneous with the particular solution. So, look, you don't have to go through all this algebra I went through. What you're having to focus on, what you want to remember is this part right here. This is how you find u1 and u2. And you start off, you're using this. Okay? You're assuming a particular solution. So you don't need to do a lot of work. It's kind of like a formula that you can use.